Okay, so what I plan to do today is that first 10 minutes I will use to review what I discussed yesterday, and then I will go on the blackboard again and try to go on from there. Okay. So this is the review of lecture 1. So let me begin by recalling what is the problem that we are trying to address. And the problem that we are trying to address is that the superstring or string perturbation theory does not always compute on-shell S matrix elements. Okay, this is the key issue. Okay. And to see this, we recall that in the language of quantum field theory, if you have to compute S matrix, okay, you have to use the LSZ prescription. Okay. And this is the LSZ prescription for computing an n-point S matrix in a quantum field theory. Namely, you start with the n-point Green's function. This is a momentum space Green's function. Okay, so the ki's are the momenta, ai's are the other quantum numbers of the external states. Then you have to multiply this by the product of the wave function renormalization factors and the inverse propagators, and then take the limit when the momentum, external momenta are on shell. Now the important point to remember is the existence of this wave function renormalization that you have to use, and also the fact that what you should use for this m, okay, the on shell limit that you take should correspond to renormalized physical mass of the external state. Okay. And the definition of z and m are contained within 2-point Green's function. Okay, so if you look at a 2-point Green's function, again a momentum space Green's function labeled by these two external quantum numbers A1 and A2. Okay. Besides this kinematic factor, overall kinematic factor that I have taken out, okay, this has a form of a smooth function in the numerator, okay, divided by a function which has a pole, okay, and it is the location of this pole in the minus k1 square plane that is precisely defined to be the physical mass, okay, and the residue at the pole is what we call the wave function renormalization factor. Okay, so the numerator is perfectly smooth, all the poles are in the denominator. Now we can compare this with what the Polyakov prescription for on-shell amplitudes will compute in a string theory. Okay. And if you were to use the same language of quantum field theory that I used last time in the previous slide, okay, it is this object. Okay. You take the n-point Green's function and multiply by this by inverse tree level propagator. Okay, you truncate, Polyakov prescription automatically inherently has this feature built in that the tree level propagators are truncated, okay, but you can clearly see the distinction between this expression over here, okay, and the previous expression over here, okay, namely the absence of the z factor, no wave function renormalization there, okay, and the fact that the limit that you are taking is when the momenta are set equal to the tree level mass squares. Okay. And as we discussed, this limit is forced on us by what is known as the worldsheet conformal invariance or BRST invariance. Okay. Namely, the limit ki square goes to minus mai square is precisely the requirement that the vertex operators that we use have to have dimension 0, 0. So this is the problem again. String amplitudes compute this, the S matrix elements require us to compute this. And the question is, in general, n is not equal to Sn. So how do we compute quantum corrected mass and S matrix elements in string theory for general external states? Okay, so this is the problem that we set out to address. Is this clear, or are there any questions? So the solution, that a tentative solution that we propose is that we generalize Polyakov prescription to compute off-shell amplitudes, and then we will use the standard quantum field theory approach to compute Sn. Okay, once we have the off-shell amplitude, okay, we can then use the LSZ formula to compute the S matrix element. And the main problem in doing this, okay, off-shell amplitudes are not new. Off-shell amplitudes have been known for quite some time. There are various proposals, okay, but the main problem is that the off-shell amplitudes depend on spurious additional worldsheet data, okay, and the spurious additional worldsheet data can come in the form of, say, a choice of worldsheet metric or the coordinate system that you use on the worksheet. And so, the goal would be to show that the physical masses and S matrix elements are independent of this additional data, even though the off-shell amplitudes do depend on them. Okay. So, we clearly know that the off-shell amplitudes are not independent of this additional data, they do depend on various spurious choices, but this is like gauge theory. Okay. In gauge theory also, you know that the off-shell Green's functions are gauge dependent. Okay. The real relevant question is the physical quantities, okay, namely the denormalized mass and the S matrix elements, are they gauge independent, or in this case are they independent of this additional data that you need for defining the off-shell Green's functions. Then we gave a definition of off-shell amplitude, okay, and this is one way of defining off-shell amplitude, namely given a Riemann surface, okay, we introduce two types of coordinates. One type of coordinate is what we call the reference coordinate, which is denoted by z, and as we saw that nothing really depends on the choice of this reference coordinate. So, this can be chosen to be anything that we like. The real relevant data on which these off-shell amplitudes depend are what are called the local coordinates. So, we introduce coordinates wi, which are local coordinates, that is used to insert the ith vertex operator into the correlator. So, wi's are coordinates around the punctures where the vertex operators are inserted, and in general if you have some reference coordinate system z, then for each puncture, ith puncture, there is a functional relationship that relates z to w. Okay, and these functions can of course be very different from at different punctures. Okay. And we use the convention that the origin of the w coordinate system gets mapped to the location of the puncture. So, fi of 0 has to satisfy that it is equal to zi, but otherwise there is no constraint on this function fi. And in terms of this, we define the on-shell, off-shell genus G endpoint amplitude. Okay. So, first of all, it involves an integral over the moduli space of genus G, moduli space of genus G Riemann surfaces with n punctures, okay, and then it involves a correlation function. Okay. In this correlation function, what we do is that you take any vertex operator. Now, these vertex operators are completely off-shell. There is no constraint that these vertex operators will have to satisfy, like being primary or dimension 0, etc. We transform these vertex operators by this conformal transformation fi, okay, that we have chosen, the local coordinate system. We take the product of all such vertex operators, n of them, multiply by appropriate ghost insertions, and take the correlation function on this Riemann surface. So, this notation, okay, basically means that this is the conformal transform of vi by fi. So, for example, if vi is a primary of dimension hh, then fi dot vi is simply given by this formula over here. Okay. More generally, the formula is more complicated if vi is not a primary. And the important point that we mentioned, and we just illustrated it with respect to the by using some examples like the tachyon 3-point function, is that this result for n depends on the choice of local coordinates wi, okay, but it is independent of the choice of reference coordinate z. And this showed that the spurious data that we have is in the choice of these FIs. Okay, that is the spurious data, and so the off-shell Green's functions do depend on the choice of these local coordinates. Okay. And the real question is the final result for physical quantities, okay, namely physical masses and S matrix elements, are they independent of the choice of local coordinate system? Okay, and this is a question that we are going to address. Okay. And I should just add that given n, okay, so what is the advantage of doing this, defining this off-shell Green's function? Okay. So, once you have defined the off-shell amplitude in this fashion, we know the relationship between Gn and An, right? We can reconstruct the tree level, the n-point off-shell Green's function by simply multiplying n by the propagators for the external lines. These are just tree level propagators for external lines. And once we have an expression for Gn off-shell, okay, we use the standard LSZ prescription for computing the physical masses and S matrix elements. Okay, so that is the philosophy, and this is a question that we will try to address. Okay, are there any questions? Yes. No, it's well, not necessarily. This Vi is okay. Well, I don't know what you mean by scalar primary. I mean, are you thinking of in terms of carrying space-time index? Vi's, Fi's are not. Say, Vi's are certainly not primaries, right? In general, Vi's are arbitrary vertex operators in for all string states. Okay, the only condition that you impose on the Vi's, okay, is that it's this, that if you take the Virasoro generators, if L0 and L0 bar are the 0 modes of the Virasoro generators, then this acting on Vi should be 0. Okay, that means it has the same conformal left and right, okay. But otherwise there is no constraint at all on the Vi's. Okay, you allow arbitrary host excitations and matter excitations, okay, because you are doing off shell, right? So general off shell state has no other constraint. Okay, so let me then stop this. I can just close this. We'll go back to the blackboard. So we said that we will try to test how things depend on the choice of local coordinates. Okay. But it turns out that for doing a systematic analysis, we have to restrict our possible choice of local coordinates. Okay, and this is what I am going to say next. Okay. So so far we introduced these local coordinates given by this function Fi, okay, or equivalently choice of Wi. We now put further restriction on the choice of local coordinates. On Wi or equivalently Fi, okay. And this is what we will call gluing compatibility, okay, and I will explain what this means. And this restriction is inspired by string field theory, okay, although I will not say anything about string field theory here. Okay, but I will explain what extra condition we need on the choice of local coordinates. So to review this, okay, I have to say a few words about Riemann surfaces. Okay. In particular, a specific operation involving Riemann surfaces, which we call plumbing fixture. So what is plumbing fixture? Okay, so let me first illustrate pictorially. So imagine that you have two Riemann surfaces with various punctures. So plumbing fixture is a procedure that allows us to join these two Riemann surfaces to form a single Riemann surface. In that process, we lose two punctures. So pictorially, what we do is that we cut out some disc around one of the punctures here, okay, and cut out some other disc around another of the punctures on this Riemann surface, okay, and then you identify these two circles. Okay. So effectively, it's like you cut out a hole here, you cut out a hole here, and you glue the two holes together. Okay. So that clearly generates a one single Riemann surface. Okay. Number of punctures is reduced by 2 because one puncture from here and one puncture from here has gone away. Okay. But that's a third Riemann surface. So it takes sigma G1 N1, sigma G2 N2, and generates another Riemann surface which has genus G1 plus G2 but number of punctures is n1 plus n2 minus 2. Okay. So, this is a physical picture, but now let me explain how it is precisely. Yes. Pardon?
These are two space time and one space time.
No, these are two-dimensional surfaces. We are using Euclidean two-dimensional surface. Right? So, these are two-dimensional Riemann surface. So, Riemann surface by definition is a two-dimensional surface, two real dimensional surface, right, which are going together. Because string world sheet is two-dimensional, right? That is why the Riemann surface is coming in. Okay. So, suppose W1 is the local coordinates around the punctures of the first surface. And similarly, W2 is the local coordinates around a puncture of sigma g to n2. So, the plumbing fixture is an identification that tells us that W1 and W2 are identified as coordinates. W1 W2 is equal to e to the minus s plus I theta, where s is a real number running from 0 to infinity and theta runs from 0 to 2 pi. Okay. So, you are cutting out the circles, two circles and gluing them, but after a scaling. Okay. The scaling is by e to the minus s, okay, and a rotation which is by the angle theta. Okay. So, W1 and W2 are identified, okay, up to the scaling and rotation. Okay. But effectively pictorially this is the effect that it has. Okay. Joining, making identification between the coordinates on this Riemann surface and the coordinates of that Riemann surface. Okay. And the thing to notice is that the coordinates that you have used, that you are going to use for this gluing, this plumbing fixture, are precisely the local coordinates that you have already chosen on the lower genus Riemann surfaces. Okay. It is not an arbitrary choice of coordinates anymore. Yes.
It's not that W1 is e to the minus s plus I theta times W2.
No.
You are
inverting. Because the point is, the reason is that as you go in the interior of the disk, right, you come outside this disk. Right? That is the picture that you want to have, right? Because you are going in from the into this disk, right? And that is the equivalent to coming out of that disk. Right? That is why one is the inverse of the other. As W1 reduces in size, W2 should increase in size. Right? Otherwise, if you go in from both sides, if you go in, right, then it is not a proper identification. Right? It is not like gluing, you do not get this geometric picture. Okay. So, this of course has not, so far we have not said anything about what condition on the choice of local coordinates it imposes, but now we are going to state this. Oh, the other thing I should have said that, so this generates a family of Riemann surfaces, right. So, this is two parameter family of Riemann surface. Why two parameter? Because A labeled by s and theta, okay, s and theta vary over real numbers. Okay. Now, you see that the choice of local coordinates on sigma g1 n1 and sigma G2 N2 automatically implies choice of local coordinates on sigma G1 plus G2 N1 plus N2 minus 2. That the Riemann surfaces which are obtained by this plumbing gluing these two together. If you already knew what are the local coordinate choices around these punctures over here and around these punctures over here, the glued Riemann surface automatically inherits that choice of local coordinates. Okay, so it's not arbitrary anymore. Okay. So this is constrained. Okay, so not arbitrary. So this one is not arbitrary. No. So when you glue, we always fix some specific punctures, right, which you can specify in some way, right. We have a family because these parameters S and theta vary, right. So as you change S, right, it's a different Riemann surface that you get, right, the modulus. So the family is basically parameters by S and theta, right. That's why you have a family, right. Not that you are choosing different punctures. Yes, but as we will see, I mean in the examples, right, typically you only choose a specific puncture and glue, right, you identify, because see, these punctures it look indistinguishable, but in any given situation these carry some external momenta, right. Okay, so the punctures are distinguished by the momenta that they carry. Okay, so you can always specify that we will only look at punctures carrying a given momentum, right, that's what we will use for gluing. Okay, and that will stick to that. Yeah, we have already decided, I mean in a given physical situation which punctures we are going to glue, right. So that's not a freedom anymore. The family comes because this is a continuous parameter family because we simply have two parameters S and theta. Yes.
At the point where you are gluing the puncture, so here you no longer have any local coordinates.
Yeah, those are not punctures anymore. Meaning you have local coordinates, those local coordinates are useful because using these local coordinates you are doing this gluing, right. If you use different local coordinates at those punctures, you will get different Riemann surface. Okay. So what kind of Riemann surface you get by this plumbing fixture depends on what local coordinates you have chosen. But after you have glued, those are not punctures anymore, right. Okay, so those are not local coordinate systems on the final Riemann surface. But these also had their associated local coordinates, those induce some local coordinate on the final Riemann surface. Okay, and the point is that those are not arbitrary, those have to be chosen precisely consistent with this plumbing fixture. Yes, because local coordinates we have already fixed, right. We are not varying the local coordinates. See, in any given situation, we fix the local coordinates, and eventually we will want to see that the final answer depends on those local coordinates, right. It's like fixing a gauge. Once you have fixed a gauge, you are not varying that anymore, right. So in that sense, you don't have a family, right. It's already a fixed quantity. If you use the different sorts of local coordinates, you will get different combinations of Riemann surfaces. It's local coordinates are infinite parameter family, right, but we have fixed it. So that's not a family anymore, right, because you are always working with a specific choice of local coordinate system. The two parameters are basically because this S and theta, right, that's what you are varying to get this two parameter family. Is this okay? That's right. Yes. Yes, because of what Riemann surfaces, the moduli of this final Riemann surface, right, will depend on what W1 and W2 you had, right. If you use different local coordinates and use the same parameters S and theta, it will correspond to a different Riemann surface, right. In particular, you can see this example. Suppose you scale W1, right, you took different local coordinates where W1 has been scaled, and then you glue. that corresponds to effectively a redefinition of S, right. But if the original S was running from 0 to infinity, the redefined S will have a different range now, right. So, the class of Riemann surfaces that we will get by this procedure will depend on what local coordinates we have chosen. Okay. So, the point is that, so this fixes the local coordinates on those Riemann surfaces which you can get by plumbing fixture. In a given situation, there may be other Riemann surfaces of the same genus, the G1 plus G2, which you do not get by this procedure. So, on those we choose the local coordinates arbitrarily, right. There is no constraint on the choice of local coordinates on those Riemann surfaces which do not come from this gluing, but those which come from this gluing, we have to make the local coordinates consistent with what we had in the lower genus surface.
Is this analog of one particle reducible diagram?
We'll come to that, right. What do you mean by, I mean, how we are going to make use of this? Okay, right now it's just a property of Riemann surface. Okay, again I think it will become clear a little later, right. Let me go ahead, I mean a few steps, right, and then we will see how, what is the rule of this gluing. I mean what exactly we mean by two Riemann surfaces cannot be obtained by gluing two conformal fixture. Okay, so what we are going to show, okay, or at least this is the goal, is that within this class of local coordinate system, right, within this restricted choice class of local coordinate systems which are compatible with this gluing, okay, the physical mass square and S matrix elements are independent of how you have chosen your original local coordinates. Okay. Now, let me come to the advantage of gluing compatibility. So, the point is that using gluing compatibility, allows us to divide the Riemann surfaces into one particle irreducible and one particle reducible Riemann surfaces. Okay, this is just a definition. Okay, we are going to define what you mean by one particle irreducible and one particle reducible, but this is what it allows us to do. Okay. And the way we make this connection, okay, is the following. The two Riemann surfaces joined by plumbing fixture essentially will be treated as if we have two amplitudes joined by propagator. Okay, we will see later that this actually goes beyond just an analogy, but right now just think of this as an analogy. If you think of it this way, okay, that whenever two Riemann surfaces get joined by a by plumbing fixture, we will think of this as if we have joined two amplitudes by a propagator. Okay. Then if we follow the rules of defining one particle irreducible and one particle reducible amplitudes in Feynman diagrams. Okay.
From the amplitude, what was the external leg? In other, there are the different external legs. You have joined this together by this propagator.
Yes, that's
it.
Yeah, exactly. Okay. So the point is that, so if you take this definition, okay, then we see that whenever we can get a Riemann surface by joining two other Riemann surfaces, okay, which are 1 pi perhaps or not even 1 pi, then we will get one particle reducible Riemann surface, otherwise we are going to get one particle irreducible Riemann surface. Okay. But again, this is still a little vague, so I will illustrate this with an example, I think then it will become clear. Okay. And the example that I will be dealing with is two-point function, because after all that is what we need for mass denormalization, right, and then we can matrix later. So, example, 2-point function. Yes.
You have a cylinder between this case and theta.
Okay, by joining I mean just using this W1 W2 equal to the minus S plus I theta, right. Joining basically means this plumbing fixture, that you take two Riemann surfaces and join them together and use this plumbing fixture to produce a third Riemann surface, right. All Riemann surfaces which can be produced that way, we will think of this as if they are one particle reducible because you have joined two lower genus surfaces. Okay. The Riemann surfaces which cannot be produced that way, okay, will be called one particle irreducible. Yes, so as I said, we will see. Let us look at the 2-point function and I think it will become clear. Okay. So, 2-point function on the torus. Okay, first take genus 1, G equal to 1. So, its torus. So, you have two punctures. This carries momentum k, this carries momentum minus k. Okay, it distinguishes the two punctures. Now, here we can declare all contributions to be one particle irreducible. Why? Because this genus 1 cannot be further subdivided into lower genus. Okay, so this cannot be obtained by gluing two lower genus surfaces. Okay. For example, this doesn't make any sense. Okay, you could ask, what about 2 punctured sphere glued to 2 punctured torus, right? Is that possible? But as we discussed last time, the 2 punctured sphere makes no sense. So, you cannot get this by gluing something like this. So, here we just declare everything to be one particle irreducible. So, declare to be 1 pi. Okay. So, at this stage you have complete freedom in choosing the local coordinate system around the 2 punctures. Now, let us go to genus 2. So, given that we have already chosen local coordinate system around 2 punctures, now we can glue 2 genus 1 Riemann surfaces. So, k minus k. So, it is clear that we can only glue a thing carrying momentum k to a thing minus k, right? Because the total momentum of course has to be conserved. Okay. So, you cut out small discs and do plumbing fixture. Then you cannot join, right? Then the momentum is not conserved. Okay, that will be identically 0. So, the point is that once you have chosen the local coordinates, this construction gives a typically not the set of all genus 2 Riemann surfaces that we could have. It will typically generate a subset of the genus 2 Riemann surfaces which we declare to be one particle reducible. Yes.
Counting would say that the first one has 2-dimensional moduli space and the second torus also has a 2-dimensional moduli space.
Yes.
The plumbing fixture has 2 parameters, so it would seem as if you have a 6-dimensional.
Exactly, yeah. So, certainly we have a 6-dimensional moduli space which is the correct dimension, right? But there is no guarantee that it will cover the whole moduli space of genus 2 Riemann surfaces. No, 6. Genus 2. Yeah. So, the point is okay. You have to also count the punctures, right? So, to begin with, we had genus 1. So, we had 2 complex dimensional moduli space. In fact, one tau and one of the z's, right? Similarly, on the other side, if you do the counting, you will find that you have the correct dimension of the genus 2 moduli space with 2 punctures. Okay. But having correct dimension does not guarantee that you will recover all the possible genus 2 Riemann surfaces. That depends on a choice of local coordinates, right? Suppose you choose the local coordinates here, okay, to be scaled by a very large number. Okay. Then effectively it will produce only those genus 2 Riemann surfaces which are connected by a very long handle. Right. So, what part you covered depends on the choice of local coordinates. Okay. So, this division into one particle reducible and one particle irreducible part, okay, is sensitive to what local coordinate system you have chosen on the original Riemann surface. Exactly. Yeah. So, you are not varying local coordinates at all in this picture. We have fixed the local coordinate system and we are just varying s and theta. So, that gives you a subset of the genus 2 Riemann surfaces. So, these are all one particle reducible, the rest are one particle irreducible. They are declared to be one particle irreducible. Is this point clear? Yes.
So here you said if the two punctures are at different momenta, it doesn't make any sense to do them. And more generally, let's say the two vertex operators correspond to different operators in the CFT, it won't make sense.
That's exactly. Right. So, there is a, you have to use the same vertex operators here to do. Okay. And then of course, you can continue this to higher genus. Yes. Yes. Well, that the zero mode counting, well, it will not be different. You have to, okay, it just depends on what, see, so far I have not even talked about putting any conformal field theory here on this, right. This is just plumbing fixture, okay, but yes, afterwards you have to do this counting because there will be zero modes also on the cylinder, okay, and then how they match up, okay. After you have done the matching, you will get exactly correct zero modes, because this is a mathematical construction of just getting the higher genus surfaces from the lower genus ones. Okay, so for genus 3, right, you can get it in different ways, right. You can get, for example, a genus 1 1pi, with a genus 1 1pi, which in turn is connected by genus 1 1pi. Okay. This now represents the effect of plumbing fixture. Okay, and you would have noticed that I am already using a notation which looks like Feynman diagrams, okay, connecting by lines, okay, but right now these lines simply mean the joining by plumbing fixture. So, once you have identified the genus 1 as the 1pi contribution, right, you can join them to form genus 3 Riemann surfaces. So, this is one set of one particle reducible genus 3 Riemann surfaces you will get, but you can get others. You can get, for example, take a genus 2 1 pi, g equal to 2, and join it to a genus 1. Okay, with k here and minus k here. Or you can have the other way. Okay, you can have genus 1 on this side, joined to genus 2 all are 1 pi on the other side. Okay. And after you have done all that, okay, these are all one particle reducible. Whatever is left over from the genus 3 moduli space, we declare as one particle reducible, or sorry, one particle irreducible. Okay. On all of these, the choice of local coordinates is completely fixed by the choice in lower genus surfaces. Right, you have no freedom. But on the one particle irreducible part, okay, there of course there is nothing from lower genus which induces a local coordinate system. So there it's up to you. Okay, you choose it arbitrarily. Okay. So there is still a lot of freedom. In fact, an infinite parameter family of freedom, because on every of these Riemann surfaces, okay, the local coordinates can be chosen in an arbitrary way, right? On every one particle irreducible Riemann surface. So you see that I said last time that string theory has the advantage that we have a single diagram instead of some or many Feynman diagrams, okay, in any given loop order. But now we are trying to give up that advantage, right? We are actually dividing the Riemann surfaces into subsectors. Yes.
Local coordinates using this function f, right?
Yes.
So this plumbing picture is equivalent to some continuity condition.
Yeah. So the continuity condition is at the boundary, right? That so this gives you a subset of the moduli space, right? Subregion, right? And you will demand the local coordinates as very continuously as you go outside the subregion into the one particle irreducible part. Right? But once you have gone across that boundary, then you let them vary in arbitrary way. Right? You let the local coordinates vary continuously with the moduli. That's the only condition that matters.
So I could have joined two things, right, rather than one. Are they contained in one PI only?
Two things meaning?
I mean, two vertex operated by plumbing.
Oh, because those we are not going to join. Those will be one particle irreducible, right? You want to join one more. Okay, so first of all, those will not have two external lines. That we are trying to construct the 2-point functions, right? So by joining two, we are not going to get extra thing. But also, when you join two, right, you don't get one particle irreducible diagram. It will be like in field theory that if you have two blobs connected by two lines, right, that is still one particle irreducible, right? Yeah, those will be contained here in principle, right? Because those we are not subtracting out. We are subtracting out only those which are joined by single lines. Right? Single plumbing fixture. Any two Riemann surfaces would be joined by single plumbing fixture. Right? That can be joined to a third Riemann surface with another plumbing fixture. But if there are two joinings between two Riemann surfaces, right, that's not one particle irreducible. Sorry, that's not one particle reducible. So that you don't have to separate out.
One to other, many choices, right?
One to other things. Two-point function you don't have any other choice, right? Yes. So hard-point function, what you can do is that instead of trying to define general one particle irreducible diagrams, you can say that I will consider one particle irreducible in a line carrying a given momentum. You don't care about whether the other think of Feynman diagrams, right? There is a notion of one particle irreducible diagrams. But you can also consider diagrams which are one particle irreducible in momentum k, right? Which means that that if you can cut a line carrying momentum k to make it into two parts, you declare it as one particle reducible. Otherwise, you declare it as one particle irreducible. Okay, cutting other lines are irrelevant. Right? So if you do that, then there is a unique choice, right? And for most of what we will do, that's what we need, right? That we always look for one particle irreducible in a single line. Right? That line you fix depending on the physical situation that you want to study, physical problem you want to study. Okay? For 2-point function, of course, there is only one momentum case, so there is no confusion. Right? There is only one way of joining. Okay. So then, the full contribution. Okay. So as I said, we gave up this nice feature that we have a single contribution at a given genus, right? A given genus contribution you are not dividing into subparts. Okay. The reason that you are doing that is because you want to combine contributions from different genera, okay, to see the effect of mass denormalization. Right? If you remember your field theory lesson, right? The way you get the pole, right, shift in the pole is that you sum over Feynman diagrams of different loop order, right? And only then you get something in a denominator. You have to organize it so that you can different genera. Okay, and for that you give nice that in a given genus there is a single contribution that you can think of it as a single contribution from Riemann surface. Okay, we divide the contribution into subparts using this feature. Okay, but with this the full contribution can be written in a formal way like this: 1 pi plus 1 pi plus where this 1 pi now contains sum of all 1 pi contributions from different genus. Okay, so this contains a part of genus 1 contribution, genus 2 contribution, genus 3 contribution. All the 1 pi contributions are dumped here. This, each of them contain again genus 1, genus 2, genus 3, etc. Okay, but joined by single plumbing fixture. This is the one that you get by joining by 2 plumbing fixtures and so on. Yes. All the bubble diagrams meaning the vacuum diagrams.
The ones like, for example, the ones with no external legs.
Those are not relevant for mass renormalization, right? So we are just counting the 2-point function, and we only count a connected diagram, right? In a field theory, you know that bubble diagrams are cancelled from numerator and denominator, right? So those we are not worried about. Okay, so this looks like the self-energy diagram, right? At least diagrammatically, it looks like self-energy diagram. Okay? But it turns out that at least in bosonic string theory and also in the Nebuchadnezzar sector of heterotic or superstring theory, this expression can be turned into a nice algebraic expression. Okay, so let me now write down that algebraic expression. So suppose we denote this, so 1 pi. Okay, so there are 2 vertex operators at 2 ends. This carries momentum k, this carries momentum minus k. Okay, but there is no other condition, no on shell condition. Okay, generally 2-point function of vertex operators. So this, let's call this f hat. This f hat is an infinite by infinite matrix, okay, because the state here can be any of the string states, right? There are infinite number of string states if you count all mass levels. Similarly, the state here can be any of the infinite number of string states. Okay, so this is an infinite by infinite matrix, okay, but you can certainly think of f hat as a 2-point function, okay, capturing all possible 2-point functions in string theory. Okay, but this includes some only over 1 particle irreducible diagrams of all genera, right? It contains genus 1, genus 2, genus 3, etc. But not the full contribution, only the genus, only the 1 particle irreducible contributions. Then this contribution 1 pi joined to another 1 pi, one can show that at least, as I said, in bosonic string theory and the Nebuchadnezzar sector of heterotic and superstring theory, this is given by f hat delta f hat. So you can understand perhaps that this is one factor of f hat, one factor of f hat, and delta is what represents the effect of plumbing fixture. Okay, the fact that you have identified coordinates on the 2 Riemann surfaces. Okay. And this actually has a nice expression for delta, okay, because after all, what is the plumbing fixture doing, right? It is gluing 2 coordinates. But it is gluing 2 coordinates after scaling and rotating, right? You scale by e to the minus s and rotate by theta, okay, then you glue them together. So delta should reflect the effect of that scaling and rotation. Okay. So delta is given by e to the minus s plus s times L0 plus L0 bar plus I theta times L0 minus L0 bar. Okay. So what does this do? This scales. L0 plus L0 bar is a scaling operator, right? It scales the coordinates, okay, and this theta L0 minus L0 bar rotates the coordinate. Okay, so you glue W1 and W2, but after you scale by e to the minus s and then rotate. And of course, then you have to integrate because you are summing over all possible Riemann surfaces, all possible s and theta. Okay. And this has a nice expression, and we put a normalization factor of 1 over 4 pi, that is for convenience. So, 1 over 2 L0 plus L0 bar delta L0 bar. Okay, so, this sets L0 equal to L0 bar, okay, and this one which comes from the S integral is the propagator. Okay. So, this again is an infinite by infinite matrix, because this is an operator, conformal field theory, but you can take arbitrary state on the left and arbitrary state on the right. Okay, so, the infinite by infinite matrix, and that is what. Okay, so, that is why how we interpret this object over here. Yes, is there a question? Yes.
For clarification, so over here then the integral will not, there will be some Riemann surfaces which will not be included. So you will say that those will not.
Those will be included here. See, anything that is not included in this is by definition here, right? Or I mean, it's either here or there will be Riemann surfaces where it's glued several times, right? Because together, see, if you look at this expression, this is a full 2-point function, right? This includes purely 1 pi. This includes 2 1 pi joined by a plumbing fixture. This includes 3 1 pi joined by 2 plumbing fixtures, and so on, right? That by definition includes all possible Riemann surfaces, right? Because you have defined 1 pi that way, right? It counts, it includes anything that cannot be generated by joining lower genus ones surfaces, right? So, it depends on, once you have defined f hat to be the contribution from 1 pi, right? After you sum everything, it includes the full 2-point function. So, the full 2-point function, let me write it here. So, the full 2-point function, yes,
can be shown in bosonic and the bosonic
NS.
and so what is the obstacle? It seems like such a general argument.
Yeah, the point of a Ramon sector, there is a picture changing operator which sits in the middle of the tube, right? I mean, this is a technical problem. Presumably it has a solution, but at least it's not completely straightforward, okay, because of this picture changing operator. NS sector doesn't have that problem. Okay, so the full 2-point function then is given. So let's call this f. This is f hat plus f hat delta f hat plus f hat delta f hat delta f hat plus etc. And full propagator. Okay, now we come to propagator. Pi. So, what is pi? Pi first of all will contain contribution from the tree level propagator, right, which is not included here. Okay, that generalizes that 1 over k square plus m square, right, that is delta. And then it will involve delta times f times delta. Because I said that the 2-point function, right, the n-point function, you remember the relationship between the Green's function and the amplitude. The Green's function and the Polyakov amplitude, right, off-shell Polyakov amplitude has this extra k square plus m square factor sitting there outside, right. That k square plus m square is nothing but delta. Okay, on any given, the delta is L0 plus L0 bar, that eigenvalue is precisely k square plus m square. Okay. So, you have to supply 2 factors of external propagators, right. So, essentially f is counting something like truncated 2-point function. Okay. But to calculate the 2-point Green's function, you have to produce some two external propagators, right, tree level propagators. That is these deltas. So, it is essentially this plus this. Okay, this is total f. And now you can substitute the expression for f that is given here. Okay. And I leave it as an exercise to check that this is 1 over delta minus f hat, or since it is a matrix, it is best to write it as inverse. It is not. It is delta inverse minus f hat inverse. Okay, just sum of this, substitute for f and sum this up, and we will find that the series expansion of this is precisely what we have there. Okay. So, the poles of this are the renormalized masses. And these are what we want to show are independent of the choice of local coordinates. Okay, 2-point function certainly does depend on the choice of local coordinates. Okay, because every definition of 1 pi amplitudes, okay, depend on the choice of local coordinates. But what we have to show is that the poles, the location of the poles, are independent of the choice of local coordinates. Right? That's the first thing, to show that the masses are independent of the choice of local coordinates. How much time do I have? 15 minutes. Okay.
What is this lines correspond to? I mean, in the string theory, I understand, but
Yes, string theory also says string theory is not. I mean, the as I said, the relationship between the Feynman amplitude, the Polyakov amplitude, and the Green's function, okay, is that the Polyakov amplitude is the analog of the truncated Green's function, right? So, to obtain the Green's function from Polyakov amplitude, you have to multiply by the inverse propagators, okay, or the multiply by the propagators, right? So, these lines are the propagators. Oh, because these are supposed to be 1 over k square plus m square, right, at a given mass level. So, this is a 3 level mass. Okay. Delta, eigenvalue of delta is precisely k square plus m square. Delta is a sorry, not eigenvalue of delta, eigenvalue of delta inverse. So, if you look at delta is what? 1 over L0 plus L0 bar, right. L0 plus L0 bar eigenvalue if you calculate on mass level m states, that is precisely k square plus m square. So, this is actually 1 over k square plus m square on every mass level, right. So, instead of saying that at given different mass levels we attach different factors, we can simply say that we attach a factor of delta to this, then depending on what mass level you are working at, that will automatically pick up the corresponding 1 over k square plus m square piece. Right, that is what I have written it as delta. Okay, if you work at a given mass level, which is what you are going to do next, then you can just write it as 1 over k square plus m square. Well, the point is that the plumbing fixture procedure, right, is a well-known construction in Riemann surfaces, right. So, that was not invented to get this, okay, but it is nicely designed, okay, so it automatically get delta as a propagator. Right. The effect of plumbing fixture, right, you can see from here, right, because the plumbing fixture is doing 2 local coordinates after scaling and rotating, right, and that effect after you integrate is precisely. Okay, so it is automatically built into in the theory of Riemann surfaces. Okay. So, we want to analyze the poles of this. Oh, maybe I should have said something else. Okay. So, what is special about F hat? So, F hat is the sum of 1 pi contributions, right. So, these get contribution from the 1 pi Riemann surfaces. Now, one special feature of 1 pi Riemann surface is that those never include degenerate Riemann surface. Okay, so let me first explain what you mean by degenerate. Degenerate Riemann surface, I take a genus 2 Riemann surface. So, degenerate Riemann surface correspond to 2 genus 1 Riemann surface joined by an infinite handle, okay, or a long handle. Okay, in the limit when the handle length goes to infinity, you call the Riemann surface degenerate. So, these are subset of the genus 2 Riemann surfaces, okay, where the it corresponds to 2 lower genus Riemann surface joined by a long handle. So these are always included in 1p R diagrams. One PR Riemann surfaces. Okay, this you can show in general, okay, that taking the handle length to be sufficiently long, you can ensure that whatever that particular Riemann surface, those family of Riemann surfaces where handle length sufficiently long, always comes from one particle reducible Riemann surface where you join 2 Riemann surfaces using plumbing fixture, okay, independently of whatever local coordinate system you had chosen. Okay. So basically the point is when you change the local coordinate system, okay, it affects the range of AC that you get. Okay, effectively 2 different choices of local coordinate system correspond to 2 different ranges of S integral. Okay. But the S equal to infinity end is always included in the one particle reducible part. Okay. So all degenerate Riemann surfaces are one particle reducible, which in turn means that these ones, 1 PI contributions, these never include degenerate Riemann surface. And this in turn can be used to show that these have no poles in K square. These are perfectly smooth as a very K square. It is not very difficult to see from the point of view of field theory, right. Suppose you have a quantum field theory. There, if you are looking for a pole in a given channel, right, suppose you are looking for a pole of the form 1 over K square plus M square. You need a single propagator in that channel, right. As long as you have one particle irreducible diagrams, okay, you never get a pole in that channel, right, because there is no single propagator that carries the momentum K. Okay, you may get branch cuts, but never any poles. So all the poles come from, in a field theory, all the poles, okay, will come from one particle reducible diagrams, okay, in that channel carrying momentum K. Okay. And this is the generalization of that statement in string theory, that because all the one particle irreducible contributions are free from degenerations, okay, these always are included in the one particle irreducible contribution. So the one particle irreducible contributions never have any poles in the K square plane. Okay, this is important because F hat, that particular property of F hat is important. Okay. Because F hat, this is what is coming in the denominator, right. So and just like in field theory, how do you solve for this, right? How do you look for solutions to this? You do it iteratively, right? You start from a leading order solution, which is K square equal to minus M square, right? You just ignore this because this starts at one loop and higher. You start with a leading order solution and then you iterate. But if this had poles, then this procedure will fail, right? Because sometimes this contribution may become larger than the leading order contribution, right? The iteration may fail. So it's important that this has no poles. Okay, is this point clear? Okay, now we are going to simplify things a bit, because you see that this is of course correct, okay, but this is an infinite by infinite matrix, right. So if you are really want to do with this, you deal with this, you have to diagonalize an infinite by infinite matrix, right, which we do not want to do. Okay. So what we can do is to work step by each mass level. Each mass level. Okay, and here I will explain what you mean by mass level. So a given mass level corresponds to states with same tree level mass. Okay, what do you expect? That in string theory, at a given mass level, right, the spectrum is highly degenerate. Okay, even at tree level mass, because you have the oscillator excitations, right? So at a given mass level, there are many states, but those are finite number of states. Okay. So you fix a given mass level and you try to diagonalize there, okay, and then you go to the next mass level and then try to diagonalize this matrix there and so on. Okay. What we have to do for this, we need to integrate out at other mass levels. Okay, and I will explain what you mean by integrate out. Okay, let me keep this as it is. So let us look at this expression over here. Right? F hat, as I have just said, has no poles. Okay, F hat is perfectly smooth. Okay, that is the way it has been constructed. But F, of course, does not share that property. Right? F has poles because it has lots of deltas. Right? And each delta is a source of pole. Right? Because there is 1 over k square plus m square factors hidden inside each delta. Right? And for s square plus m square with m square running over all mass levels. Okay. But suppose you want to work at mass level m. Let us define an operator delta bar. Okay. Let me not add for mass level m. Suppose you want to work at mass level m. We define an operator delta bar. What you do there is that you take delta, okay, and subtract from this a term of the form 1 over k square plus m square becomes a projection operator, where this is the projection operator mass. Okay, so this is a projection operator into finite dimensional subspace, because at mass level m there are only a finite number of states. Okay, not all on shell, there are off shell, not all primaries, right? Primaries, secondaries, but nevertheless there is a finite number of states. So you project onto that subspace and you subtract off 1 over k square plus m square. So this delta bar has the property, okay, that it has lots of poles, okay, as a function of k square, okay, but no pole at k square equal to minus m square, okay, for this fixed mass, because those poles have been just subtracted out by hand. Okay, so if you think of delta as a block diagonal matrix, okay, 1 over L0 plus L0 bar, it has 1 over k square plus m1 square, 1 over k square plus m2 square, 1 over k square plus m3 square and so on, okay, for different mass levels. We just subtract off one block, okay, from delta and define that to be delta bar. And now we define an f bar, which is the analog of f, but with delta replaced by delta bar. And if you want to think of it pictorially, it is like 1 pi plus 2 1 pi but this time connected by a different line, okay, not delta but delta bar. This represents the effect of delta bar. All of these are delta bars.
some particle at mass m.
Yes, that's right.
And if you don't mind, why are we subtracting that contribution from the property?
Because all of these will not declare as a new one particle irreducible. Okay? Because this is like integrating out all the heavy states, right? Suppose you are a light state, right? You are just integrating out the propagators of the heavy states, right? But here it's not light and heavy, it's mass level m versus mass level not equal to m. Okay? We just sum up all those and declare them as our some one particle irreducible prime, right? The main point is that this object that you get this way has no poles at k square equal to minus m square. It has poles at other mass levels, because the delta bar of course has poles at other mass levels, but not at k square equal to minus m square. So if you are interested in studying the mass renormalization at the k square equal to minus m square level, right, the corrections of course will be perturbative, so they are small, they will keep you inside k square nearly equal to minus m square regime. Then we can work with f bar. No, yeah, they will also contribute in this, but they still don't have poles at k square equal to minus m square, right? That's why it's not like division into light and heavy. Okay, it's like the division into light and heavy, but it's not that we are keeping all the light modes, right? At a given mass level, we just integrate out everything other than that mass level. So I'll leave it as a simple exercise. Okay, again it's not hard. Check that propagator restricted to mass level m Okay, what do you mean by this? All we mean by this is that we considered Pm phi Pm. Okay, we had this full propagator phi, right? There, it's capital phi. We have the same propagator, but now we restrict to states of mass level m on both sides. So that this becomes a finite dimensional matrix now, right? Because at mass level m there are only finite number of states. So this is given by k square plus m square minus this f bar and then there is two projection of point. Okay, this is the analog of this. Okay. Instead of delta inverse, because we are restricted to mass level m, okay, we get k square plus m square. Okay. But you have to make sure that you integrate out all the heavy modes or not heavy modes, all the modes other than those at mass level m, and that basically converts f hat to this quantity f bar. Okay, this is an identity. In fact, you can just do an algebraic manipulation of that expression and so this has the advantage that this is now a finite dimensional matrix. And you want to check that the poles of this are independent of the choice of local coordinates. Okay, this whole construction, okay, so far has depended on the choice of local coordinates, because this division into one particle irreducible, one particle reducible diagram itself is very much dependent on that property, okay, that specification. Okay. But our goal will be to show that the physical masses that you compute by looking at the poles of this are independent of the choice of local coordinates. Okay, so I guess I have finished my time, so we will do that next time.
Couple of questions. Yeah.
Suppose, okay, it's a vague aside and maybe a stupid question, but if I want to use the plumbing fixture for Kutkowski kind of stuff, yes, then suppose I'm generating the higher Riemann surfaces by plumbing the lower Riemann surfaces. So, does this procedure construct all the degrees of freedom of the higher Riemann surfaces, or this is not sufficient?
By all the degrees of freedom, you mean whether you can get all possible diagrams, all possible Riemann surfaces? Typically, nobody has been able to find. So you have to start with some basic 1pi vortices, right? Basic vortices, in terms of which you build everything. Right? So typically, what happens is that at any stage, if you don't have gotten something, you declare them to be 1pi. Okay? If you are asking whether you can have a finite number of 1pi vortices and you can get everything from there, okay, that has not been achieved so far. Okay? And I think there are some general arguments in the context of string field theory, which basically says that you have to keep adding more and more 1pi vortices to get all the cutting all the possible Riemann surfaces, okay, and of a given genus. Right. So the answer is that you cannot start with a finite number of 1pi vortices and generate everything. Okay, at least there is no known procedure for that. Okay. If you are allowing arbitrary number of 1pi vortices, then of course you can generate it, right? Because at any genus, whatever is not obtained from gluing lower genus surfaces, you just declare them to be 1pi, right, and add them as extra terms.